And so we're looking at this problem with video screen tension, and we're told that a manufacturer has high resolution video terminals that must be controlled with the tension. If you take a look at what's given to us, we are told that we have a random sample of 20 screens. So that means random is taken care of. 20, that's bad news. No central limit there, no CLT. So what am I going to have to do? I'm going to have to take those 20 numbers and I'm going to have to input them into my calculator. And I'm going to input them in L1. Now what I like to do is I can run a 1var stats, and that's going to allow me to find the sample mean, x bar, and the sample standard deviation, s of x. So that's what I'm going to look at there. And then I'm going to actually look at the graphs beyond that. So be aware that since our sample size is less than 20, we have to find a new way of checking for normality. So we have to construct a 90% confidence interval, and we have our context of what mu is, the mean tension. So we have our state right there. We want to estimate the true mean mu tension of all the video terminals at a 90% confidence level. That meets everything in the checklist. Now the next part is what's the plan step. Now when you're dealing with the plan step, you want to make sure you include your opening statement. If the conditions are met, what are we going to do? We're going to use a one sample t interval to estimate mu. We're going to have to name our inference procedure. So make sure you are looking at that opening statement. If the conditions are met. Okay, now what interval we're going to do? One sample t, because we don't know the population standard deviation. And what are we trying to estimate? We're trying to estimate the population mean mu. So that opening statement is important. Make sure you're providing all three of those in the opening statement. Random was told to us. Now normal, we already said, sample size is less than 30. It was 20, so we cannot use central limit theorem. How sad. So what we're going to have to do is we are going to have to inspect the data. That's where it says you must check whether it's reasonable to believe the population is normal. So we're going to use our calculators. And you can see right here what I'm writing down is stat plot. And we're going to have three graphs that you can look at. You can look at a histogram. You can look at a box plot. One of those, well, both of those deal with symmetry. You should do one of the two. Then the one you should always do is normality. You want to look at a normal probability plot to see if you have an approximately linear pattern. So try and do 2 out of the 3. If you're going to do 2 out of the 3, you want to make sure you do either a histogram or a box plot, because those both deal with symmetry. And you want to do a always normal probability plot. So let's look at how to put those in our calculator and do that.
So we were doing the tension problem, and a lot of the graphs are given to us, and we want to look at how do we do it if we're not given the graphs, and we're going to use our calculator. So you can see if I go to stat, I go to edit, I have all the screens on there, the tensions of the screens, all 20, and since our sample size is less than 20, can't do central limit theorem, so we have to inspect the data. Now, I'm going to quickly jump to the do step, which is where we have the x bar and the standard deviation. So remember, I can go to stat, calc, 1var stats, and choose my first list. If I do that, that will give me my x bar, which in the problem itself we saw was 306.3, and it gives me my standard deviation of the sample, s of x, as 36.2. So that's where we got those in the problem. Now, if we're looking at the plan step, our sample size, we can see, is less than 30, so we cannot use the central limit theorem. So we have to inspect the graphs, inspect the data. So in that case, I'm going to go to second, y equals, and I have stat plot. I'm going to turn on stat plot, and we're going to examine the 3 types of graphs you can use. First one is a histogram. And so I have the histogram. I'm going to hit zoom, and I'm going to choose option 9 for zoom stat. If I do that, I see the histogram. Now, I'm not a fan of the histogram because the box widths are determined for you. I can't control them, but you can see what's going on there. I'm a fan of, if I hit second stat plot, I go down to type, and I'm going to choose this one, which is a box plot, which will show me outliers. Do not choose this one because that will not show you the outliers. This one will tell me if I have any. I like the box plot because it's a better way of looking at shape. So again, I'm going to do zoom 9. Right there, I can see that box plot looks approximately symmetrical. I could not see that as well with the histogram, and that's my opinion. So I like looking for symmetry based off of the box plot. But symmetry does not tell us normality. Can we use it? But Good news is normal graphs are symmetrical, so at least have that qualification down. So to determine, okay, does it fit the ability to assess normality, use normality as well, I need to assess the normality using a normal probability plot, which is that last one. And if I do this, I'm going to leave everything the same, and I'm going to hit zoom 9. That represents a normal probability plot, which is the plot of the z-scores. If that plot is approximately linear, there's no strong curve pattern to it. If it's approximately linear, we can use normal approximations, and we can see that's what we did in this problem. So that is what we're looking at on how to do these 3 graphs, is input the data in your list. You might as well run the 1var stats. That's going to give you your x bar and your s of x, which you're going to need anyway. And then you need to look at, I say, 2 of the graphs. I like to look at box plots, and I like to look at normal probability. Do not do box plots and histograms, because those are both used for symmetry. So you can use histograms or box plots, but you need to look at always the normal probability plot to see if there's a linear pattern.
So as you can see, what we did is we looked at the stat plots, we looked at the box plots, normal probability plots, and what that did was tell us symmetry, and it told us if we're looking at approximately linear. So now that we have those down, we can say, hey, it's safe to approximate normality. And we check the independent condition, and since it's safe to assume there's more than 200 video terminals produced this day, and we're sampling without replacement. So from the 1 variable statistics in our calculator, we found the x bar and the s of x. So you can run the 1var stats L1, and you would get your information, and that gives you your x bar and gives you standard deviation of the statistic. Sample size of 20 gives us a degrees of freedom of 19, and we're looking at that part of table B, and we're looking at the 90% confidence interval. So we should get a t-star of about 1.729. So we can write that down. Now we can construct the confidence interval. So we have all the information, make sure we plug everything in, and you can see what the final interval is going to be. But we're going to make sure we kind of go through this. Your statistics are from that 1var stats. We state our degrees of freedom, we state our critical value, where we found it, and we're going to state our standard error. Standard error is your standard deviation of the statistic divided by the square root of your sample size. So you can see that in the work. Confidence interval, when you state that, you want to make sure you kind of look at the margin of error. Look at what we're dealing with there, which would be 14, and then use that with the calculation, and that will give you your interval for the answer. And we can go to the conclusion step. We are 90% confident that the interval from blank to blank, and you have the units, captures the true mean tension in the entire batch of video terminals produced that day. The state confidence level, we want to state the interval, and we want to state what parameter we're trying to capture. And please make sure you say capture, don't forget the context. And so in this example, we're looking at the healing of skin wounds in newts. And we see here that we have a random sample of 18 newts. We have the units that we're looking at as well, our context. 18, that's sad. Can't use the central limit theorem. That means we're probably going to have to inspect the data for this one. So we can take that data, we'll put it in our calculators as we go through. But let's first kind of go through the whole process. Our state is we want to look at it. We're interested in estimating mu, the population mean healing rate of newts with 95% confidence. So we have the parameter as symbol and words, we have the population, and we have our percent confidence. So now that we have, that's the state part. You can write state there instead of define the parameter of interest. That's your state part of inference. We're going to take those, we're going to put them in our calculator, and we're going to run a 1var stats. And that's going to allow us to inspect what our sample mean is and our sample standard deviation is. And we're going to look at inspecting the data visually. And we're going to go ahead and look at our graphs, our either histogram, our box plot, or our normal probability plot. So we're going to look at those to determine what's going to be going on in the problem. So we have 1var stats, that gives us our sample mean, gives us our sample standard deviation. Stat plot, that's going to tell us, can we use normal approximations? That's what we want to do. Can we approximate normality for this? So we'll let this finish up. So now that we have that, let's go on to the plan step. So we're going to check the conditions. If they are met, we're going to construct. We got to define our inference procedure. A one sample t interval for mu. It was stated that we do have random. We're trying to estimate mu. 18 newts. Now if we inspect the data, you know what? Let's go inspect the data.
So now we're looking at the other example. We're looking at the newts example. And so we go through this, same idea. I go to stat edit. I have the measured healing rate in millionths of a meter per hour for all of the newts. And notice our sample size is less than 30. So therefore I'm going to have to inspect the data to see if we can meet the normal condition. Can't use central limit theorem. But again, what we did is we went to stat, one var stats, L1, and that is going to give me what our mean was, about 25.6 or 27, so 25.7, and it gave us our standard deviation about 8.3. So we have our statistics that we need for the do step. So that's good. I can go there as soon as I finish the plan step. So for the plan step, what I'm going to do is I'm going to hit second stat plot. I'm going to turn it on, and I'm going to look for symmetry. So I'm going to use the box plot. That's just me. I like to do it, so I'm going to hit zoom, and again, I'm going to go to option 9, zoom stat. Right there, there's slight skewness, not strong skewness, so there's slight skewness, I can see, but beyond that, no outliers. So since the sample size is between 15 and 30, I'm okay with slight skewness. As soon as we drop below 15, no skewness. 15 to 30, slight is okay. But let me also check, so I can see the symmetry there, but I'm also going to look at the normality. If I look at the normal probability plot, so I'm going to hit second stat plot, go back, and I'm going to use this one. So again, I'm going to do zoom, make sure I can type the number 9 or go down to 9 and hit enter. So again, I look. Does there appear to be an approximately linear pattern? And there does appear to be approximately linear pattern, so I can say, okay, you know, the box plot shows slight skewness, and this is stuff I would write down. The box plot shows slight skewness, but that's okay. We can proceed because the sample size is between 15 and 30. Looking at the normal probability plot, I can see it has an approximate linear pattern, so therefore I can use approximate normal calculations. And so that was the do step that we did, and the plan step combined with the calculator. So that is how you use your calculator.
So now you can see how we inspected the data. We looked at it with the calculator as we went through, and we looked at the graphs. I say do at least 2 of the 3. I like looking at the box plot. I like looking at the normal probability plot. Those are my 2 favorite ones. You could do the histogram, but those 2 together show you symmetry. The normal probability plot, if it has an approximate linear pattern, is going to allow you to say, hey, I can approximate normality. So you can see what's written down there, and of course we do have, I'll scroll down, the independence condition met as well. So symmetry for the box plot and histogram, and then normal probability plot, approximate linear pattern is going to tell you whether you're dealing with normal or not. Those are you want to look at. It is safe to assume there's more likely than 180 newts, by the way. So independence is met. And so we can look at the next part of this, and that's the do step. So 18 means our degrees of freedom was 17. And we can go look at table B. I'm going to tell you what's going on. N equals 18. T star for 95% confidence interval for this would be 2.110. So we can go and plug in all the information given to us. Remember, our X bar and our S of X would have been found from our 1 var stats in the calculator. So make sure that you know, you go to stat calc 1 var stats L1 and get the information. We have everything else to plug in to get our interval, and then we can interpret. We are 95% confident the interval from 21.53 to 29.81 micrometers per hour captures mu. You can use the Greek letter mu, the true mean healing time, and there's your context of what we're dealing with. So that is what's going on there. There's our table B. If we wanted to take a look at how I found it, I have degrees of freedom of 17. I have 95% confidence. which means I'm going to go to that row of 17 and that column of 95% confidence. So 95% confidence would be 0.025 in each tail. So I'm in that column and I'm in that row, and you can see where I got the 2.110 from in that case. So that's what we're looking at newts. Now let's continue on.
So we can also use our calculator for full-on t intervals. So if we go to stat and we go to tests, notice I can keep scrolling down and I see right there t interval. That's what we're trying to do, is a t interval. Now there's two ways of me doing it. I can use the data, and this is what we... So we're now on the part of using t procedures wisely. And this is really what the whole last part of the lesson has been, is if you have a sample size greater than or equal to 30, you can use central limit theorem. That's the way it's been since chapter 7 for us, where you're dealing with means. But if it's not, that's where t procedures are robust. We can still perform calculations where they do not fit perfectly into that greater than or equal to 30 or from a normal population. And so that's what we're going to keep in mind. I'm going to hit play on this. What I want you to realize is there's a handout that you were given that goes through this on the bottom part of what's going on. Is look at that handout as well as the outline of what's looking at. So if it's robust, it can be used when we're not told if the population is normal and when your sample size is less than 30. So certain criteria has to be met, and we've already examined that criteria with our calculator. You know, we have to look at the symmetry in the box plot. We have to look at everything that's going on with the normal probability plot if it's going to be linear. Now you can see here it says except when you have outliers or strong skewness. And that's really, really important. And key word there is strong skewness. And the reason why is that's bad for normality. So let me stop this for a second. Is if you have outliers, can't be normal at all. So therefore, can't do anything with it. Now, strong skewness, notice the word strong. And that's really important because if it has a slight skewness, and you saw that in the other video, if your sample size is between 15 and 30, and that's what's on the handout for you, slight skewness is okay, but no outliers. You can't have outliers because then that's really bad. It's affecting the data. But when you have strong skewness, that's really bad. You can't have strong skewness, and it's going to be strong right skewed. Well, you can't do anything with that if your sample size is less than 30. So we're going to I say look at that handout to get an idea as well to make sense of these slides at the end. So be aware, a large sample size, by the way, just means central limit theorem. So we're okay with large sample sizes. It's when it's less than 30, it gets a little iffy. And that's kind of where this slide is, and I tried to make it a little bit better on the handout. Let's start from the bottom up. Large samples is your central limit theorem. And so you have that idea. Now the next thing you're going to look at is, okay, what if I have a sample size of at least 15? And if I'm looking at a sample size of at least 15, that means between 15 and 30. And when that happens, I cannot, see the word except, I would underline that, I cannot have outliers, I cannot have strong skewness. You cannot have those if you have a sample size between 15 and 30. So no outliers, no strong skewness. Slight skewness, okay. Strong, not so much. So then you go into the idea of what if it's less than 15? And if it's less than 15, I mean, it's got to be like perfect. So you can have no skewness at all. You can have no outliers. If it is clearly skewed, or if there are outliers, you can't do it because your sample size is so small. So it has to be roughly symmetric, single peak, no skewness, no outliers. And like I said, this is kind of outlined on that handout a little bit better. So keep that in mind. It breaks apart with the idea of over 30, central limit theorem. Between 15 and 30, okay, you still have a pretty good size. All right, so we'll allow slight skewness, but you better not have outliers because that's not good for the data. And you get less than 15. I mean, that's a really small sample size. So your sample has to be really good. So hey, you know what? Make it symmetric and make it single peaked. And no outliers, no skewness. And if that happens, all right, let's continue with the t procedures and they can be used. So our t distributions our t-star can be used when it's less than 30 if it meets these criteria. And that's kind of what we're looking at in this. So we can keep that in mind. And so you can see right now, what's going on is I have written down here is there can be no skewness at all if it's less than 15. Don't allow skewness. However, if it is between 15 and 30, slight skewness is okay. But both of them cannot have outliers. So it doesn't matter which it is. So in other words, if your sample size is less than 30, no outliers. No outliers allowed at all. Then you look at skewness, which is why I like to look at the box plot. So this is really kind of going through, and hold on one second. This is really kind of going through the calculator idea of why do I look at the box plot first? Is, well, that's going to tell me if I have any outliers. So if I have any outliers, can't continue. That's why I like the box plot. And so, okay, what if it doesn't show me any outliers? Okay, good, I have no outliers, so now I have to figure out, if it's between 15 and 30 for the sample size, is it symmetric or slightly skewed? Because if so, good news. If it's less than 15, is it symmetric? Does it look like it's going to be just perfectly symmetric for us and no skewness at all? Do we have, when we're looking at normal probability plot, a linear pattern? So that's kind of what you're going through in this case. So this goes through what we analyzed in the video when we had our sample sizes less than 15. And we had, sample sizes between 15 and 30. We didn't do one of less than 15 because it has to be perfect, no outliers and symmetric. So when you're dealing with this, less than 30, inspect the data. Put it in the calculator, look at the box plot or histogram, look at the normal probability plot, and see if these criteria are met. And so that is lesson 8.3 to finish off. Did before, and so I have my data. And for the new problem, we were trying to figure out what's going on, and I believe we were using a 95% confidence level. So if I'm looking at a 95% confidence level, I have my new data inputted, and I can just straight down to calculate. And this is what's really nice about this. It gives you your X bar, your S of X, and your interval. Done. But the only issue is that is your do step. That is not your plan step. But the good news is it gives you what you have for your answer. Great for multiple choice, by the way. Really great for multiple choice. But notice it did not inspect the data. So you have to inspect the data for it. So that's the new problem based off of data given to you. That's actually not bad. It calculates for you. I wonder if I went to stat tests and go down to t-interval, and what does stats mean? So I'm going to click this. Well, look at this. Stats means if you were given information. So if I were told what my average was, so let's say the average for grades on the test was an 82%. And I said, hey, the standard deviation of the grades was 2.7% for a sample size of, and I'm just going to go ahead and use 45. Central limit theorem there would allow us to approximate normality. And then you have what's your confidence level, and you go through and you can calculate it. Same idea, it gives you the X bar, the S of X, and it gives you your sample size of 45. Now, this is the one where if we go to this, and I use X bar, let's say this, but let's say I had 950. If you were using table B and you had 950, you would have to round down. But if you're using your calculator, you could say your degrees of freedom is 949, and it's going to give you the t-interval based off of that particular degrees of freedom. So this is why I'm saying, hey, if you're going to use the calculator, you have to be very specific. But if I'm going to use table B, and I'll show you what table B would have been, if I would have done table B, I would have had to input a degrees of freedom of 100, which means I would have just had to have a sample size of 101. And we can look at that, and we'll see it is a different answer. So we need to be specific. If you are going to use t-interval, you need to make sure you use the appropriate sample size that is given to you. And it's going to calculate it based off of that. If you're going to use table B, you need to be consistent with table B. So that is how you do your calculator. Now, another thing about your calculator, which is interesting, if I go to stat tests and you look at that, you have the t-interval. That's where you're going to perform the test. But if I want to go backwards, I can go to second vars, distribution. Notice it says inverse t. Now, if you're dealing with inverse t, you're trying to find the outside of the distribution, so you're trying to find the t-score. Here's where you do area to the left. So area in the tail. If I want to do area in the tail and I have a 90% confidence interval, each tail will have 0.05. If I want to deal with, then you have your degrees of freedom, and let's say I have a sample size of 50, my degrees of freedom is 49. That will give me my critical value associated with that. Now, if I have inverse t again, and let's do a 95% confidence level, so that'd be 0.025 in each tail. But what if I have a sample size of, let's say, let's say 900. If I have a sample size of 900, my degrees of freedom is 899. This would be my critical value. But if I were using table B and I had a sample size of 900, I'd have to round down to 100 for my degrees of freedom. Now, if I do that, notice there is a difference in the critical values. This is why I say if you're going to use your calculator, you are sticking with the calculator. You would have to use the negative 1.96. If you're going to use table B, then you're going to have to stick with table B and use negative 1.98. So it doesn't matter which one you do, but inverse t is area in the tail, which by the way is on the top of your table B, and then comma your degrees of freedom. So that allows us to go through and find that information.